Hi everyone, welcome to lecture number 4. And in this video, I'll be talking about an optimization on a quick union using union by rank method. Okay, why do we need this? What is the use of this thing? And stuff like that we'll discuss. Just to be sure, just to make you clear, rank here means the size of the graph, the size of the graph. Okay. So in the worst case, what we can have is we can have a skewed graph like this, where every vertex is connected to some other vertex like this, and the vertex is the parent of the below vertex. Okay. For example, G is the parent for H, F is the parent for this, E is the parent for that, and so on. And before I tell you about all those things, it is better for me to show you the pseudocode first, and we'll walk through this implementation by following the pseudocode. Okay. So in the start, what we do is we declare a root array. And in this case, every node initially is a root for itself. We also maintain a rank array. Why? Because rank array is the kind of operation or the operation on quick union, which will help us to optimize quick union. Okay. Initially, the rank for every node is 1. Why 1? Because it tells us that the height of that node is 1. Okay. And this is the find operations that we have. We have a loop here, and we will continuously ascend the loop. We'll continuously ascend the vertex to find the root node, and this can take on the order of n time in the worst case if our graph is skewed, something like this, okay, where we have to ascend from the bottom to the top to find the root node, okay. And this is the union operation we have here. We find the root for the first vertex, root for the second vertex, and if they are not equal, then we proceed with the union by rank, okay. Now, I'll talk about this thing a bit afterwards, but this is the core crux of union by rank, which is an optimization on quick union, okay. Why do we need this? Why do we need union by rank, and how is it even helpful, okay? So let us answer that question first. We see here that we have two graphs, two different components, and the height of this one is 2, and the height of this one is 3. Okay. What will happen if I add this graph? What will happen if I try to, connect? Let us suppose if I try to connect 0 and 4. In that case, there are two ways. Hey, if I have to connect 0 and 4, take this component and merge it with this component. Okay. Or take this component and merge it with this component. The neat picture overall, it will remain something like this, where both of them are connected. But what is the difference? What is the difference if I merge this component into that component? And what is the difference if I merge this component into that component? The difference is pretty much inevitable. It is pretty much inevitable in the sense that the height will increase or decrease depending upon which component you are trying to merge. For example, if I try to merge this component with a larger height into a component which already had a smaller height of 2, what will happen is we'll be able to merge something like this: 0, 1, 2, and 3. What it does is it increases the height of the previous component by how much? 1, 2, 3, 4, by a difference of 2, correct? Initially it was 2 and now it is 4. So the difference of height is 2. So we see that the height of the new component gets increased when we merge a component with a longer height into a component of a smaller height, okay? And this is troublesome. Why? Because it will affect our find operation. Because find operation, it asks us to continuously ascend until you find the root, okay? And if I have to find the root for 3 in this case, so I will have to make a continuous ascending to reach the prime root, which is 4 in this case, okay? So in this case, the height of the original component, which was just 2, has increased to 4. And since the height increased, it will affect our find operation, and it will be much more exhaustive time-wise, okay? Now let us take a look at what will happen if I merge 4 and 5 into this component, okay? We'll take a look at this. We'll take a look at that. Just give me 1 second. Okay. Now, let us merge 4 and 5, okay? I'm assuming I'm merging 0 and 4, and I'm assuming that 0 is the root of 4. So if that happens, the entire tree will look something like this. This is the 4, and this is the 5, okay? So what was the initial height? The initial height was 3. What is the current height after merging? It is still 3, okay? So we noticed that there was no increase in height when we merged a component with a smaller height into a component with a larger height, okay? And that effectively saves our time in find operation. And I think this is pretty much obvious. A longer height will absorb the smaller height, okay? But something like this. But if I try to merge a longer height into a smaller height, something like this, so the height of the net component it will increase, right? So yeah, that is what it is happening here. And this is why we avoid the other way merging, where we merge the larger component into smaller component. Okay, we prefer what we prefer to merge the smaller height component into the longer height component, and this is what is getting done here. If you look at this thing, if the rank of the first node is greater than the rank of the second node, in that case we merge the rank of the smaller one, second one, with the first one. Okay, if the rank of the second node is greater than the rank of the first node, in that case, we merge the smaller one, which is the first one, with the second one. If they are both equal, we merge either of them. I have merged the second one with the first one, and I've increased the height of the or the rank of the first one by one. Okay. For example, in this case, as you can see here, let me choose a different color. Yeah. The height of 0 is 1, the height of 1 is 1, and if I have merged them and I've considered 0 as the root node, so the height will become 2, and the rank of 0, according to this formula, it will increase by 1. Okay. And again, time complexity, if we talk about that, it is order of n. Find operation is it is again order of n, and is connected, it is again order of n. So what did we accomplish here? We accomplished that we avoided a further ascending, right? By tackling with find operation. How did we avoid that? We avoid that using the union by rank method. Okay, so yeah, that's it. That's it about union by rank. Again, the crux of this thing is that we merge a graph with a small height into a graph with a larger height, so that we avoid further ascending. Okay, when we try to find the root of any node. Okay, yeah. So that's it about this thing. In the next video, I will show you the code and I will walk you through an example on lead code. Oops, my bad. Yeah, okay. So in the next video, I will show you the code and I will walk you through the example on the lead code. Till then, take care of yourself and bye-bye.